This is the start of the recording. Well, volume check. And put that there. Yeah. All right. 90 seconds. 90 seconds. All right. Extend the size of that. Oh, that's better. There we go. There we go. All right. Let's do that. Hide that. And do that. Okay. 50 seconds. Do. 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hello, good morning. It is 11 a.m. on Wednesday, April 22nd. Happy Earth Day. I've been thinking about this for a couple of weeks now, but I was thinking that I don't know, like it's either cut my own hair or I should bleach it and dye it. I don't know what color, so maybe you should throw your suggestion for color in the chat box or something like that. Okay. Day 2 on induction. So need to prove. Let's switch the marker to be a little thicker here. So need to prove a statement that looks like this for all n in positive integers, some predicate. So if you need to prove that, we have our traditional approach to proving this is, select an arbitrary positive integer, or have the reader select rather, and then you prove the p of n part. That's kind of the usual way, but we have a new way to prove this, right? This alternate method. The alternate way now involves step 1, prove p of 1, and step 2, prove a different for all that starts the same for all k in positive integers. If p of k, then p of k plus 1. Right? So this first thingy here, proving p of 1, is called the base case, or the base step, or whatever you want. Okay, and then this second thingy is called the inductive step. With the p of k part, sometimes it's helpful to be able to refer to it. That's called the inductive hypothesis. So this is, the general idea is think about like dominoes is sort of this I hope is a helpful analogy for what's trying to happen. But to put sort of better words to it, what's really going on here, the key to understanding this new method of induction is understand that an infinite number of uses of modus ponens occurs. That's what's going on, actually, right? So you prove p of 1, and then having proved the for all statement that's here, you end up with p of 1 implies p of 2, and p of 2 implies p of 3, and p of 3 implies p of 4, and p of 4 implies p of 5, and so on. So it sets off this kind of chain reaction, because if you prove p1 is true on its own, awesome, then because p1 implies p of 2, then you have p of 2, and so on and so forth. But that base case needs to be proved on its own. If you just prove the inductive step, it's just a bunch of dominoes that are all standing next to each other. Somebody's got to tip that first domino. So this is not this induction isn't a magic trick. isn't magic. So just like when first learning proof by cases, I think when proof by cases, when what's really happening with proof by cases is unclear, it just seems like magic. And I said it then when we were first looking at proof by cases. I'm like, that's not magic. It's like I want you to convince yourself or talk to me about why this really works. Same deal here. Like this really works, and you need to know what this is to be able to modify it. Know how this works to be able to modify it. So I'd like to kind of revisit the theorem we had just started yesterday and did not have a full amount of time for. So I sorry to kind of restart it, but I think we'll be okay here. So for all integers n greater than or equal to 5. Oh, nobody has a color suggestion for after bleaching my hair what color I should dye it. But all right. So for all integers n greater than or equal to 5, the inequality 2. Where did the marker go? Oh, this is not good. There we go. Sorry, pen just kind of ran out for a second. 2n squared greater than quantity n plus 1 squared holds. Okay, so just before starting the proof here, just to clarify that p of n is the predicate. 2n squared greater than n plus 1 quantity squared. So this thingy boxed right there is the predicate p of n for this problem. Because the theorem doesn't start for all integers n greater than or equal to 1, but rather 5, the base case is different, right? So in starting the proof, the base case is to prove p of 5 being true on its own, right? So, and plugging in, I'll write it directly under the box here. Plugging in, is this true? We verified kind of yesterday, right, that this is the left side simplifies to 50 and the right side simplifies to 36. So it checks out. There's no variables here, so that's fairly fortunate. The inductive step requires a little bit more work. So for the inductive step, let me kind of write this right here, inductive step, sort of in the same level of indentation, right? So the inductive step, we've got to modify, sorry to scroll up, but like over here, this inductive step started for all positive integers k. We've got to now go with for all integers greater than or equal to 5. So even this step, it's let k greater than or equal to 5 be an arbitrary integer. Now we want to still prove that p of k implies p of k plus 1. So we'll suppose p of k. Supposing p of k means, well, that's p of n in the box up here. We just, for p of k, we just need to replace all the n's with k's, right? So we'll suppose that 2 times k squared is greater than quantity k plus 1 squared. That's p of k. It looks just like p of n, just replacing all the n's with k's. And then we want to show p of k plus 1. So we want to show replacing all the n's up here with k plus 1s. We want to show 2 times quantity k plus 1 squared is greater than, replacing n again with k plus 1, we have k plus 1 plus 1. I'll just write that as a k plus 2 quantity squared. So just to annotate what's going on here a little bit, this right there is p of k. And then this here is p of k plus 1. So I know it's not very usual for us to be proving inequalities. We've been doing a lot of equality proving, but you know, same general principle. So I'm going to start with one side and then show that that's bigger than the other side. So I'm going to start with 2 times quantity k plus 1 squared. Well, what's that equal to? We can expand out the k plus 1 times k plus 1 and have k squared plus 2k plus 1. And then that's distributing the 2, so 2k squared plus 4k plus 2. I'm trying to always look for an opportunity to use the inductive hypothesis. So this inductive hypothesis up here, it's P of k, the thing that's under the first underlined thing in blue. This is a fact that we know currently for a fixed value of k. I don't want you to think of k as being I don't want you to think of k as being a variable. K is some integer that's bigger than or equal to 5 that we did not pick. The reader of the proof picked. So what's underlined here, I don't see a variable, right? Like there's this number, k might be 5, k might be 55. But if you ever see a 2k squared, that is guaranteed to be bigger than k plus 1 quantity squared. And look, right here is that 2k squared. So this text here should be greater than k plus 1 quantity squared plus, and then we still need to count for the 4k plus 2. This is usually the place where there's some confusion, so I want to have you stare at that for a moment, see if we're okay with this. So this text in green, the first green circled thing is bigger than the second green circled thing. And so if you prefer to write a side argument, you could start with 2k squared is greater than k plus 1 quantity squared. We know that. That's just that. And then you can add to both sides, if you prefer to say it this way, 4k plus 2 to both sides. And adding to both sides of an inequality keeps the direction of the alligator symbol. If you prefer that, this text right here, the action of having added 4k plus 2 to both sides, is just kind of written in a vertical format, so it looks a little funky perhaps, but that's all that happened. Okay, so I'll just maybe wait for a moment, see are we okay with that step? Well, if so, then I'm going to suggest we do the following, which is then to expand out this k plus 1 quantity squared and have k squared plus 2k plus 1 plus 4k plus 2. And here's where it's a little tough to have the argument kind of all on the fly, but I will, let's see here, k squared plus, so it turns out that this is going to be equal to k plus 2 quantity squared plus the rest of the fluff, which is 2k minus 1. This step requires some staring at for a moment. It's just a lot of algebra happened all at once, really. So you'll notice, like in this first term here, the k plus, so there's a k squared, there's a 4k, so that's over there. Then there's a constant 4, but we only had a constant 3 available, which is why there's a minus 1. I mean, a lot of this creative work is done in the name of being able to get to our final goal of k plus 2 quantity squared. So that's why it looks as funky as it does. Off to the side, I have this side argument that I want to make right now, that namely, I want to note that 2k minus 1 should be bigger than 2 times 5 minus 1, and this is because k is greater than or equal to 5, right? So up here, k was something that we don't have control over what k is, other than we know that the reader picked k to be something bigger than 5. So if k is bigger than or equal to 5, this is true. If you want to think of it, you start with k is greater than or equal to 5, multiply by 2 on both sides, take the resulting inequality, subtract 1 on both sides. But the way that we apply this right now is to say we'll keep this first term as is, and then copy the inequality symbol right here, and replace the 2k minus 1 here with this 2 times 5 minus 1. Okay, and then we can go ahead and simplify. So this expression is equal to, so k plus 2 quantity squared plus 9. And the thing is, if you want, this number is bigger than just dropping the plus 9, right? So you have a plus 9 there, it should be a bigger number. But in the end, we started with this thingy and applied the inductive hypothesis here by inductive hypothesis, and eventually ended up with this number is either equal to or bigger than bigger than or equal to, we keep having these, all the alligator signs point the direction needed to show that 2 times quantity k plus 1 squared is eventually, it is bigger than k plus 2 quantity squared, which is what we wanted to show up there. And so that actually ends our proof by induction. Let's just kind of wait for a moment, see if we've got anything that needs to be brought up. See if we have any questions. It's a little much because a lot of ingenuity and a lot of creativity in some of the algebraic manipulation comes up. Question came. I still don't understand why we put in 5 for k. We didn't put in 5 for k. We just argued, starting with k is greater than or equal to 5, we argue that this is true. Right? Because if you start with k is greater than or equal to 5, multiplying by 2 on both sides, you have 2k is greater than or equal to 2 times 5. And then if you subtract 1 on both sides of this inequality, you have 2k minus 1 is greater than or equal to 2 times 5 minus 1. So we made use of the fact that k is greater than or equal to 5 because that was part of the setup of how the theorem was stated in the first place. It actually turns out that for smaller values of n, this inequality doesn't even hold. So that's why we had to start at 5. Does that sort of address it a little bit? I hope. So the fact that the inequality, whether the variables are n's or k's, it doesn't hold in general. This inequality doesn't hold in general. You can actually, in fact, if you want to, graph the two parabolas, right? Graph y equals 2x squared and graph y equals x plus 1 quantity squared. And the two parabolas kind of cross each other in two different places. So the final crossing happens at some point, and then if you look at x starting at 5 and beyond, then there's no more crossings that occur. Then one parabola always remains above the other. Yeah, so it's not so much that we're using it in all the final 3 steps. What's going on is the fact that k is greater than or equal to 5, which leads to this, allows you to replace that 2k minus 1, which is here, with 2 times 5 minus 1. But then to make that replacement, you have a greater than or equal to sign. Again, if like earlier you didn't like how the argument was first presented here, what you could do is start with, so we have this is true, and then to this inequality right here, you can add k plus 2 quantity squared to both sides. So you have k plus 2 quantity squared plus what was there before, the 2k minus 1, greater than or equal to k plus 2 quantity squared, plus, and then what was there before, 2 times 5 minus 1. So this is written sort of in a more traditional horizontal format, but that's all this inequality symbol right here is saying. It's the same information presented vertically. So ultimately, the validity of this inequality right there, this one, ultimately stemmed back to requiring k to be greater than or equal to 5 up here, because this led to that, led to that, led to eventually to that. So we'll just kind of wait and see, is that maybe better? Okay, then how do we go from greater than or equal to just greater than? Yeah, good question. So the thing is, let's call this thingy right here. Can I just call it a capital A for a minute? And what we have then, and then the next one here, I'll call this one B, I'll call the next one C. What we have is A equals B equals C greater than D equals E equals F greater than or equal to G equals H greater than I. If I'm just copying all the symbols I saw here kind of in order. But the thing is, if A is a certain number and then B is the same number and C is equal to that and D is less money, right? It's like, so C is a certain number of dollar bills, and then what's D? Just you keep some of the money and then the rest of the money on the table is D. And then E is the same amount of money as D, and F is the same amount of money as E, and G is either the same amount of money or smaller, because F is bigger than or equal to G. Ultimately, in the end, A has to be bigger than I. That's all, right? Because you've got these two inequality signs that are strict. So, of course, we could say A is greater than or equal to I, but more strongly, we actually know that A is greater than I here. So it's the fact that all the alligators that they appear all point the same direction. They're all, anytime you have an inequality symbol, it's either a greater than or a greater than or equal to. So ultimately, in the end, this thingy has to be bigger than that one, right? This thingy has to be bigger than that. Does that answer that part? These are good questions, so let's keep them going. And I think the other thing about a question like this is the algebra that you're seeing here, it's actually not all that bad. It's just organized in a fashion that you don't normally see it. And I think the other thing to do in a question like this right now is to think about if you want to revisit the algebra and kind of write it your own way, cool. But I wrote it this way, at least in part, to make you think about some of the algebra, but also let's kind of separate. There's the algebra argument side of things versus the overall what's going on with proof by induction. So if it's something like I'm not sure I buy all the algebra, but if the algebra is good, then the argument works. Then there's that side of things too. At the same time, I'm not trying to stop any questions, any further questions if anybody has any they want to bring up. I think because I don't see anything for the moment. Let me know if that changes. I would like to try another one, just another proof by induction for another example. So new question, although this new question is going to involve bringing up a definition. And this is, I will not quiz you on this definition, but it's one that I want you to know, and it applies in a lot of these sorts of problems. So look it up as you need it. But let f sub n denote the Fibonacci sequence. I'm sure you've seen the sequence around, but I just want to clarify that the first number in the sequence is a 1, the second number in the sequence is a 1, and then all the following numbers, to get the nth number generally speaking, what you do is you take the previous two numbers, so f sub n plus 1, and you take f sub n minus 1 and f sub n minus 2, and you add those together. So most of the time, right, when n is starting with the third number, so yeah, for the n, little n here stands for which position in the Fibonacci sequence. When you're looking at the third position and further, what you do is you just add the previous two numbers. That's what this line is trying to say, right? It's what's called a recursive definition, because it's using, to get a certain number in the sequence, you need to use the previous two values, right? You've all seen this sequence, this like 1, 1, and then your third numbers add the previous two. 1 plus 1 is 2. Then to get the next number, you add this 1 and this 2 to get a 3 here. And then to get the next number, right there, you add the previous two numbers, you get a 5, right? This adding of the previous two numbers, the arrow pointing to the 2, the arrow pointing to the 3, those are added together to give 5. That's not just made up. It's not a secret I have. It's informed by this line right here. Okay, so this is what the Fibonacci sequence starts to look like. 8, 13, right, 21, that sequence. And what I'd like to do, in addition, is for the what's the word I'm trying to for words, just for notational convenience for the next problem, I'd like to define alpha. Let alpha be the positive solution to the equation x squared equals x plus 1. Okay, this is a quadratic equation, right? In order to solve this, factoring does not work out by hand anyway. What you end up doing is getting all terms on one side, quadratic formula. So I'll just let you know, just as a comment, I'll let you know what alpha is. So this was found using the quadratic formula. If it's the positive solution, so it turns out that the two solutions happen to be 1 plus or minus root 5 over 2, but if you put the minus out of the plus or minus, you have a negative solution. So this is, the point is, if you graph the parabola y equals x squared minus x minus 1, there's a positive x-intercept and there's a negative x-intercept. And by alpha, we just mean this number. So every time you see an alpha, think this fraction, Alpha is not a variable. Alpha is a number. I just don't want to write that fraction all the time. What I'd like to do is work on this task together. I'd like to prove for all n in positive integers that the nth Fibonacci number, according to how the sequence was defined up there, is less than or equal to this number alpha raised to the n minus 1 power. That's what I'd like to prove together. So if you try a standard proof of this, like nothing seems to work out, and that's why induction seems to be a good idea to try. So we'll try to prove by induction. Try proof by induction. And in trying to do this, we should look at the base case. So the base case is, we need to prove that P of 1 is true. So if, by the way, this, let me box it in a new color here. If that box thing, this is P of n, then to prove P of 1, we want to show, just replace every n in the green box with a 1. We want to show f sub 1 is less than or equal to alpha to the 1 minus 1, right? Everything that's in the green box is written replacing all the n's with 1's. Well, is this true? Well, there's technically actually no variables over here. I know it looks like there's f and alpha as letters, but f sub 1, scrolling back up there, it was defined to be 1. So the left side simplifies to be a 1. Is that less than or equal to question mark alpha to the 1 minus 1? Well, we know what number alpha is here, but it doesn't actually all that matter that much because this is alpha to the 0th power, right? And you know that raised to the 0th power, what you have is a 1. So this checks out. What we needed was ultimately 1 less than or equal to 1. And 1 is less than or equal to 1. So that works. For the inductive step, right? So I'll try to organize the work at the same indentation level here. For the inductive step, remember that this statement of the inductive step starts with a for all. So we should let k be positive integer arbitrary. And then in the inductive step, aside from that for all, there's an implication. So we assume P of k. In other words, the green box thing, that's P of n, so replace all the n's with k. So assume that f sub k is less than or equal to alpha raised to the k minus 1 power. Right? So that's P of k. And then we want to show P of k plus 1, meaning we should write down what's in the green box again, but replace every n with a k plus 1. So we'll have f sub k plus 1 less than or equal to alpha to the, let's see, k plus 1, then minus 1. So how about we just simplify that k, the plus 1 minus 1? That. We have not done, of course, this proof yet, but are we clear with the outline of this before moving on? I know this is all just a little bit, there's a lot of notation it seems, but the f sub whatevers are actually all numbers in the end. I wrote out the first several of them, and alpha is a number. Alpha is this fraction up here. So I know it's a little strange, but this is what we want to show right here, let's start working on one side or the other. So I'll start with the f sub k plus 1. And then my goal is to try to, have equalses or less than or equals symbols to eventually get to, whoops, the wrong one. I was circling the wrong, to eventually get to this alpha to the k here. That's the goal, right? To have something like that. So to do this, first of all, f sub k plus 1, there is a little, I'm going to leave some details a little bit to you to think about, but the key point is most of the time, f sub k plus 1, it's going to follow this. So plug in, for the n, plug in a k plus 1. In other words, just generally speaking, what's going to happen is to get f sub k plus 1, well, to get a term in the Fibonacci sequence, you add the term before. So this is the k plus 1 term, right? Position number k plus 1. So you take the kth number and the k minus 1th number, k minus 1st number, I guess, and you add them together. Now the thing is, we already know, remember what was assumed over here, we already know that f sub k is less than or equal to alpha to the k minus 1. So this part we can replace with alpha to the power k minus 1, but because we're replacing f sub k with something that we don't know it's equal, we just know that this thingy is bigger. That's why the symbol's already this, and then we have a plus f sub k minus 1. But now, I mean, our goal is to eventually have over here, right? The goal is to eventually have here like a less than or equal to or some symbol, and then an alpha to the k, which is found right there in our want to show line. But we don't have anything going for us, because what do we do with this? What do we do with f sub k minus 1? We don't know anything about it. All we have, if you look at, don't look above the base case, all we have is k is a positive integer. We have this inequality about f sub k. We don't know anything about f sub k minus 1. We don't have any fact given to us about this. So I will say that we are stuck. We have no info. As my notes say, we have no info about f sub k minus 1. So here's what we need. We need a stronger inductive hypothesis. So sorry to work you through that thought process, but trying to do mathematical induction the way it was introduced yesterday doesn't actually work on this question. But there's a small tweak to the method that really does work. This tweak maybe isn't so small. It's a large enough tweak that this variation of the original method goes by a new name. So since we don't have any information about f sub k minus 1, let's think of, I'm going to introduce to you a method that will give you information about f sub k minus 1. Had we applied this new method that we're about to introduce in the first place, we would not have gotten stuck. But I needed you to see what getting stuck looked like. This is just like, in calculus, I'm doing u substitution right now, and students need to see what picking the wrong u for their integral looks like. So, you had to see what getting stuck looks like. So here's a new method, though. So to prove for all n in positive integers, p of n, so same general setup. You need to prove a statement that looks like that, just like before, and then the name of the method I'll just introduce right now. It's called strong induction. I don't actually very much like the name of it. Most people don't once you learn what's going on, but I think the name comes from this right there, stronger inductive hypothesis. The new method has a base case and an inductive step as well. The base case is just as you expect, nothing changes here, so you prove p of 1. Nothing changes about the base case. The thing that's different is the inductive step looks different. So the inductive step is now you prove, still there's a quantifier here, so I'll just stick with a k. I don't know if I have a k in my notes. I put an n in my notes. I'll just use a k here, just to change it up. So the thing you prove starts with a quantifier again, and then what you have again is an implication, but the implication looks different. It's now if p of 1 and p of 2 and p of 3 and so on and so forth, and all the way up until you get to p of k, then p of k plus 1. So earlier, if we cut out, we'll use a new color here. If we cut out this part, p of 1 and p of 2 and p of 3 and da-da-da-da-da, all the way up to right before p of k, so up to p of k minus 1, I guess. If we cut that stuff out, that's the induction we already talked about. That's yesterday's induction. This new one has this huge and. There are k facts that have been anded together. Of course, when you split this up, you have k separate facts. So you have all of this stuff. You have many pieces of information, and this part is still now called your inductive hypothesis. So using this new method of induction, which is called strong induction, your inductive hypothesis is much larger, and it splits up immediately into k separate facts. So you have a lot of extra information going for you that you can use if you'd like to. And you might say, wait a second, we heard an argument for why yesterday yesterday's induction, let's call it standard induction. You heard yesterday, like, okay, I buy that. Maybe, this thing with the falling dominoes, but it's like you're just changing this. Like you're just picking up extra information for free. How is this even allowed, right? So I'd like to try to give you an idea before we dig in, like a cartoon idea of why this new method why is it valid at all? Because it seems like this seems like I'm like cheating somehow, right? So I'll say that part A, the base case, is like the first person's, person number one's like, I'm gonna have a party, right? One person says they'll have a party. They'll host the party, in other words, right? But like, a party's no fun if that's the only person going to the party, right? So then the idea is like, it's something like, what if, person one needs to convince somebody else to go to the party, and the second person's like, I don't know, and person one's like, no, come on, it'll be fun. And so then, person two is easy to convince, like, okay, since you're hosting the party, I'll go to your party, and then, you don't want a party with just two people. You want a third person. So the third person, you go up to somebody like, okay, person number three, you should come to this party, but they don't want to go. They're like, well, so and so and so and so are going. Like these two other people are already going. So then you can convince the third person to go. And then what about P of 4? The idea of P of 4 being true, the analogy is like the fourth person goes to the party and is convinced because there's already three other people who are going, right? So this kind of the general idea is persons numbered 1 through k convince person k plus 1 to go to the party. And that has this ripple effect, right? So if the first 10 people, they've decided to go to the party, and 10 people kind of crowd around the 11th person and say, come on, you should go to the party, it'll be fun. And that 11th person like, okay, I'll go. And then, so this is kind of, I don't know, somewhat realistic kind of way that maybe sometimes parties grow out of hand. But in this fashion, if you follow this model through, then everybody ends up going to the party. Everybody that has a number assigned to them like this. So let's do the proof this way, right? So our proof using strong induction. So still P of n is as before. This is the predicate as we had earlier. F sub n less or equal to alpha to the n minus 1. I know it was a while back, but this was our predicate earlier. The base case, we already proved it actually, because in our failed attempt earlier, we already proved P of 1, namely, so we just proved it earlier. It's all just that F sub 1 less than or equal to alpha to the 1 minus 1, because this was, as I remind you just a moment ago, our proof came from the fact that 1 is less than or equal to 1. The new thing we're doing, the new inductive step, this is what's new now, is we should, since it starts with a for all, let k in set of positive integers be arbitrary. And then here's the difference, right? So the if-then that we're looking at is different. In fact, the if part has lots of facts. There's k facts. So we assume P of 1 and P of 2 and P of 3 and P of 4, right? Like we assume all these things leading all the way up to P of k, and then we want to show P of k plus 1. So just to note, since we know P of k, and I'm sorry to do this, I'm going to scroll back up, but P of k, if I just copy it from a moment ago, was right over back here, right? P of k was this thing that we assumed. So I'll copy paste this, sorry to do that. I guess I didn't need to do that. I should, let's not do that. Let's just argue it again. So P of n is in the box here. So P of k is f sub k less than or equal to alpha to the k minus 1. We also know, we know P of k minus 1. So f sub k minus 1 less than or equal to alpha to the k minus 2. We also know p k minus 2, so f sub k minus 2 less than or equal to alpha to the k minus 3, and so on. We've got a lot of facts. And the fact that we want to show p of k plus 1, as we already stated right in this line, but in other words, we want to show f sub k plus 1 is less than or equal to alpha to the k. So this want to show line also we had mentioned earlier. But here's the neat thing that occurs now. Here's the thing where earlier, so to prove this inequality, let's start with the left side of it. F sub k plus 1. Well, this, due to how the Fibonacci sequence is defined, a term is found by adding together the two previous terms. So to get the k plus 1th term, you add the kth term together with the k minus first term. We already said a thing like that a moment ago. The thing that we did earlier was f sub k can get replaced with a alpha to the k minus 1 as long as you replace with an inequality symbol. So alpha to the k minus 1. That we did earlier. The problem was earlier all we could do was we were stuck writing f sub k minus 1 here. Now we don't have to do that. Now we also have this fact. Right? This fact we did not, that I just boxed, we did not have that earlier when we did standard induction. But because f sub k minus 1, this is smaller than or equal to alpha to the k minus 2, we can write that there. Now I'd like to do a little bit of algebra. I would like to actually factor out from here alpha to the power k minus 2. And if you do that, you'll have to have an alpha plus 1 inside parentheses. You just check that. Multiplying things with the same base, you add the exponents. So k minus 2 added to the hidden 1 exponent there. That'll get you your k minus 1. Yeah, so I think that factoring works. I also want to remind you of a thing we said a while back, so excuse me while I scroll for just a moment and grab how alpha was defined. Alpha was the positive solution to this equation. I'm going to just paste this down here so that we can stare at it. Just a reminder that alpha is the positive solution to this equation. But the point is, if you have a solution to this equation, it means that this number alpha satisfies this equation. In other words, alpha squared is equal to alpha plus 1, right? That's what it means to be a solution to an equation. You plug in that number. Remember, alpha is a number. If you plug that number in for all the variables, the left and right side need to equal. That's how you have a solution to an equation. And this tells us that alpha plus 1 can be replaced with alpha squared, which we're going to do right now. I'm copying the alpha to the k minus 2 power, but this alpha plus 1 right there, we get to now replace it with alpha squared. And now, multiplying two things with the same base, so you get to add the exponents, and you get here alpha to the k. So if you look through this line, I know the arguments came from different places, but we do have a proof here. So f sub k plus 1 is, in the end, let's see, where's the symbol? Oh, the only inequality is there, so we better adopt the inequality in the same direction, is less than or equal to alpha to the k. And that is exactly what we wanted to prove. That's back here, right? So we have a check mark for that. This is a proof by strong induction. So let's pause here and see if there's questions. Because there usually are. I know this is a little strange at first. I mean, while people are thinking of questions, I'll just say the difference between strong induction and the standard original induction from yesterday is that in strong induction, your inductive hypothesis converts into k facts. We didn't use all k facts, did we? Actually, of the k facts, which I, out of laziness, only wrote down 3 of them and some dots over here, we only used 2 out of the k facts. But the point is, we needed 2 of these k facts. Just having 1 of them, which is what standard induction would have given us wasn't enough to get anywhere. Okay, couple questions coming in. So we have p of 1 and p of 2, etc. How does that transfer to p of k minus 1? Um, yeah, so it's I think yeah, the answer to that question is it's half philosophical in that um, this k, when we write a sentence like let k in positive integers be arbitrary, we don't have control over what k is. Remember, we're proving this for all statement the standard way at that point, and so when we write that, we relinquish control, we give up control of what k is to the reader. So I get this idea of trying to transfer a fact we have, but if we like sit to think about like what's really happening in proof, the moment this sentence is written, k is fixed. We don't keep varying the value of k. If we could vary the value of k, I get this argument. Why not just transfer that fact over to a different p of k for a different of whatever, right? But it's this idea that k is fixed, right? The reader had fixed that, and then the next. I hope that sort of addresses it. It's semi-philosophical, but not really. I mean, this kind of I get where you're going with it, but it digs into just how the kind of the law of proof works here. And then the other thing is strong induction useful in cases that do not require recursive definitions. Yeah, yes. The short answer is yes. Can I think of one right off the top of my head? No, unfortunately. Like my next example you'll see in the notes is another recursive definitions one because it's another one about the Fibonacci sequence. I will say that almost every proof involving the Fibonacci sequence does use a strong induction instead of standard induction. But are there examples of strong induction applying without where there's no recursiveness in any of the any of the definitions? Yeah, there are. I am aware of these. I just can't think of one off the top of my head. So I hope that. But it's a nice question though, like to kind of try to go like, oh, is that a time it applies? Probably. If you see a recursive definition, I would my go-to thought is strong induction, but at the same time, it's not some kind of if and only if either. There's going to be strong induction is used for some non-recursive. Let me see if I can go dig one up and like maybe post something about it. If I can go remember to do that. Okay. How about I know it's 9 minutes, but like, should we maybe just start on another one? See where we get. I don't want to rush through it, but just see where we get on another strong induction question just to get an exposure to another problem. So if f sub n is the nth Fibonacci number, then for all n in positive integers, f sub n plus 6 is equal to 4 times f sub n plus 3 plus f sub n. So this is quite a statement here, and I'll just note that our predicate p of n is f sub n plus 6 equals 4 times f sub n plus 3 plus f sub n. So this is kind of funky. It just almost seems unbelievable that this is actually even true. That somehow you take one Fibonacci number and then you jump 3 spots away, take that number, but first multiply by 4, you add the results, and that ends up being, if you jump 3 more spots away. I mean, there's all kinds of funky things that seem to be going on here. So to prove this, we're going to apply strong induction. First of all, the base case. So the base case just needs to be proved kind of outright, so we want to show p of 1 is true. And so this requires working out some details that if you plug in, so we want to show, plugging in 1 for all the n's, we want to show f sub 7 equals 4 times f sub 4 plus f sub 1, right? If you plug in a 1 for every n, I just already simplified the 1 plus 6 to a 7, and the 1 plus 3 to a 4. All the subscripts I've simplified. And then you just need to work out, like go through the first 7 terms of the Fibonacci sequence, and I'll spare you the details right now. But f sub 7 is equal to 13. And then what about 4 times f sub 4 plus f sub 1? Well, 4 times the fourth Fibonacci number happens to be 3. And then, let me see here. Yeah, and then plus a 1, and then that ends up equaling 13 as well. Cool, so these match. Okay, again, base case, so P of 1, right? Base case actually usually doesn't have variables, which is real fortunate. The more difficult part is the inductive step, right? So inductive step, remember that the inductive step starts for all positive integers k or whatever. I mean, k is a placeholder variable, but I'll go ahead and use k. So let k in positive integers be arbitrary. So the reader is, we can almost think of this as a random choice, right? Like we don't get to pick what k is. The reader is going to pick whatever positive integer they want to be k, and it's fixed. So we can't keep changing it. It's not a variable. And then we're going to suppose, now if the reader had picked k to be a big number, let's say they picked k to be 100, then we are now going to suppose 100 facts as being true. We're going to suppose P of 1 and P of 2 and P of 3 and so on and so forth, all the way up to P of 100. But to have a way to write that, instead of writing it 100, I'm just going to write up to P of k. Right? So we suppose these are true, and we want to show P of k plus 1 is true. Okay, so this part right there, supposing these k separate facts, I guess, I just already broke apart the and here, right? So this is the inductive hypothesis. And we want to what we want to show here, let's just write this, want to show P of k plus 1 a different way. That's, again, boxed all the way up here is P of n. So let's plug in, to get P of k plus 1, we need to plug in a k plus 1 for every n. So we want to show f sub, plug in k plus 1. Okay, so k plus 1 for the n, and then a plus 6. So k plus 7, right? F sub k plus 7 equals 4 times f sub k plus 4 plus f sub k plus 1. That down here in this box is obtained by taking the box up at the top and replacing every n with a k plus 1. So if this is what we want to be true, then we should, do some usual things here of, okay, f sub k plus 7. Let's start with the left side. But then due to how the Fibonacci sequence is defined in this recursive manner, the k plus 7th number in the sequence is the k plus 6th number added to the k plus 5th number. Right? That's just what happens in the Fibonacci sequence. Each number is found by adding the two previous. And then here's the thing. We should have maybe written that I did leave a little space here. So P sub k being true, by the way, right? That's one of the facts we assumed is true. So we know P of k is true. In other words, we know, and that's the box that's still kind of right at the top up here. Just replace all the n's with k. So we know f sub k plus, so up there at the top, n is a variable, right? N is the placeholder variable inside the predicate. Right now we're plugging in this specific k that we don't know what k is, but it's a specific number that the reader picked. So f sub k plus 6 equals 4 times f sub k plus 3 plus f sub k. We know this fact. We also know p of k minus 1. That's kind of hidden in the dots. So we know f sub k plus 5 is equal to 4 times f sub k plus 2 plus f sub k minus 1. So check out how this is useful now, right? So of these k facts, the first fact and second fact and so on are probably not all that useful for us. I'm just looking at the last fact we know, p sub k, and the fact right before that, p sub k minus 1, or p of k minus 1. Yeah, so p of k and p of k minus 1 are these two boxed facts that we know, and we can apply them immediately. Because take a look. The first term, f sub k plus 6, is equal to, and we replace with 4 times f sub k plus 3 plus f sub k. And then this next, right, so what's underlined here in red is equal to what's right there. That's the red box. Then I'll use blue. This f sub k plus 5, due to the blue box here, we can replace this with 4 times f sub k plus 2 plus f sub k minus 1. And now, let's think about what our goal is. Oh yeah, we started with this. We're trying to get to that. So here's what I think we should do. We should take the two terms that have 4 and factor out a 4. So 4 times quantity f sub k plus 3 plus f sub k plus 2. And then the two terms amongst our 4 terms that don't have a 4, let's just write them f sub k plus f sub k minus 1. Now check this out. What's in parentheses? What is f sub k plus 2 added to f sub k plus 3? Well, following what's going on in the Fibonacci sequence, these are two consecutive numbers in the sequence. So it should be the next number in the sequence, f sub k plus 4. And then finally, if you take the k minus 1th number in the list and you add it to the kth number in the list, you should get the k plus 1 number in the list. And that is exactly what's right there, right? So we have now our proof that f sub k plus 7 really is 4 times f sub k plus 4 plus f sub k plus 1. So this completes this proof by strong induction. And this what's going on here is it's something that's actually true. So if you want, I mean, it won't be a proof, but it's kind of neat to go Google the Fibonacci sequence and just verify if this fact seems to be true. For just pick a couple values of n and see if this really works. And it's kind of bizarre that it does, but it's true. That's what I got. I'm just about running out of time, so I'll stick around if there are questions. But otherwise, I will see you for office hours 1:10 to 3:10 today on Wednesday.